We continue with our lessons in chemical kinetics, and in today's lesson we're going to look at the integrated rate laws. So we're going to run through the zero order reaction, and then we do the first order reaction, the second order reaction, and the equations of these reactions are these. So this is the equation for the zero order reaction, and the half-life is this one. For the first order reaction, the equation is this, and the half-life is that, even this and that. So if this lesson was all about knowing the formulas, then we can say we're done, because you've seen the formulas. But there is more to that. We're going to derive these formulas, and then we even get to run through practice questions. And we'll start with the first order reaction. I'll start with the first, second, and we end with the zero order reaction. So getting started with it, with the first order reaction. So we can have a quick recap. So this is actually lesson 4 in our chemical kinetics series. So in lesson 3 we had an introduction to the rate law. So we looked at the rate law and we talked about the two types. So we said there is one type of rate which depends on time, and then the other one depends on the change of concentration with time. So let me just quickly show you this. Okay, so there is this is what we looked at. So in this documented lesson we discussed how the rate depends on concentration, and that's what's called the differential rate law. And then in this lesson now we're going to focus on the integrated rate laws. So I gave an example of a differential rate law is this. The integrated rate law will look like this. We're going to derive. So that's on that. So if you don't have this lesson, this document, you can inbox me on WhatsApp. So you can use this line. Okay, so we get started now. Okay, so we know the rate law. So the rate, we said, it goes with a K. This is the rate constant, and the concentration. So this is taking it that we only have one concentration. So if this is our reaction, like we have A is reacting to give maybe B. So the rate law is given by K and then the concentration. So what I want to highlight here is that if we have a first order reaction, it means in the rate law the power is 1. Okay, so this is the rate law of a first order reaction, the general thing. And then we can quickly have an overview of like the second order reaction. In the second order reaction we would have rate would be equal to K, and then the concentration of A will be raised to the power 2. That is the second order. And then for the zero order, when deriving, we're going to use this. So A will be power 0 for the zero order. So these are just basics which we can take note of. So now we go to derive in the first order reaction. Okay, so we're going to consider a general reaction. We'll say A is reacting to give, we can say anything, to give B. So B doesn't matter here. So under some books we'll just write to give products, a certain product. So this is the general reaction. So let's write the rate law. What is the rate law of this reaction? So we know to say that the rate law, so we just write rate. So the rate is equal to K A, we can say power 1, because this is the first order reaction, so power 1. So this is the rate law. And then now we're going to write yet another rate, which we call the rate expression. That was from lesson 3, yeah, in the previous document. So what is the rate expression? So you remember the rate expression depends, it is related to the balancing coefficient. So the rate expression, which we can also call the rate of formation of A. So the rate of formation is now we know that the rate of formation is simply the change in concentration with respect to time. So we used to write it like this: change in concentration of A with respect to the change in time. So with respect to the change in time. So this is the rate expression, and this is the rate law. So now on the rate expression, we're now going to further say it's negative. So this is the rate of disappearance. So we'll say this change, we'll use dA. So remember, this was the differential rate equation, the differential rate law. So by differential rate law, it has some roots in differentiating. So very soon, a few minutes from now, on the integrated rate law. So this integrated rate law, you know integration from mathematics. Yeah, so I'm not going to dive deeper into integration. So the rate law is mathematical. We have the differential rate law for differentiating and the integrated rate law for integration. So this or change in A, we can write it as dA, like that. So meaning change in A, and then we say over dt, which is the change in the time. Yeah, so this is the rate expression of the rate law and the rate expression. So what we're going to do now is equate the two. So we're going to say the rate, so the rate law, will be equated to the rate expression. Yeah, so rate law is equal to rate expression. So what is the rate law? Here the rate law, it is so let's start with the rate expression. Let's start with writing this d change in A with respect to the change in time. Okay, so there, that is the change in time dt. So this will be equal to, what is the rate law? The rate law is K, and then this is our A, and then we raise this to power 1. we're dealing with the first order reaction. Okay, and then from here now, our aim will simply to have the concentrations to be together on one side. This concentration, you should make sure it finds its way to the right hand side. So what are going, firstly, let's get rid of the negative. It should be that side. So we say we can multiply this side by -1. So meaning even this side we multiply by -1. Yeah, so if what you do on one side you also do to the right, to the other side, then you haven't changed anything. So negative and negative, it's positive. So we're going to have the change in A with respect to dt. So this will be equal to, so now this side we're now going to have a negative, so negative k, and then we'll have this. So at this point, how do I explain this? Very simpler. So we're going to cross multiply. So remember, want to have this concentration to be this side. Yeah, so we say cross multiply, so this means there's over 1. So dA times 1, it will just be d the change in the change in A. So this will be equal to -k. So we have this -k here, and then we have the concentration A. So we have that A. So we have this, and then dt at the end, because we've cross multiplied. And then yeah, so this is a lengthy process just to show you how we're forming the formula. So we divide by the concentration in A. So even here we divide by the concentration in A, and then our resulting form now, we're going to have dA there over the concentration of A, and then this will be equal to -k. Is that k? Yeah. So this is -k. The A cancels, and then we'll remain with dt. Okay. So at this point we're going to say, so since we have these things on one side now, so this is the part where we apply integration. This is where the name comes from, integrated rate law. So we have we have dA, concentration in A, over that concentration in A. So this is equal to -k, and then we have dt. So now let's integrate. So starting with the right hand side, so we're going to apply what are called the definite integrals. Yeah, so one thing to take note of, this is a constant k. So we don't differentiate or integrate a constant. Yeah, so we separate it away. Even the negative, we separate it. So meaning we're going to put an integral symbol here. And then we can take note that we're going to have time from t is equal to 0. So here we're going to say t is equal to 0 up to a particular point where we have a certain time from 0 to a particular time. So we've just separated this, and then even here we apply the definite integral. So we're going to say from the initial concentration 0 there, so that is supposed to be 0. So from the initial concentration up to the final concentration. Okay, so now here we won't go into now how do you differentiate. So at this point, this is why you get to, on the part of integration, this is why we get to say when you differentiate this, you are going to have, it's simply going to be the same. This cathene, it is just going to disappear, but we're going to say this is ln. We're going to have ln that concentration. So this is like the final concentration at a particular time. So this is initial all the way up to final. So we're going to have concentration at a particular time over the initial concentration where we're starting from. So we'll see how the questions will come. You'll be given initial concentration is this. Okay, so this is O. It's not confusing. So you just saw how we made this the subject, like we cross multiplied and then we divided. And then at this point you just show that we have applied the definite integral, and then when you integrate we're going to have ln A at a particular time over t. So this will be equal to the constant negative k, and then when we differentiate here from 0 up to a particular point, we're just going to remain with a t. Yeah, so in short here what has happened on is getting rid of the d. So you can see here the d went, we've remained with this. Yeah, so we're going to say this will be negative k is already here, and then we're remaining with t. So this is the first order reaction, the integrated rate law. And then we can simplify it further. We know from mathematics, and by the way we're going to do calculus, we'll go more advanced so that we understand everything. Yeah, so from logarithms we know that when we're dividing, it simply means we're subtracting. So where we have ln A, so this is ln A at a particular point. So since we have a fraction, it simply means we're subtracting. So it means ln A at a particular time minus ln A, the initial concentration. So this will be equal to negative kt. And then we can make ln A the subject. So we're going to say ln A so this is ln A is equal to negative kt. So this minus it can go to the other side. So we're going to have, it will be equal to negative kt plus this now ln A initial. Yeah, so finally this is the first integrated rate law. Yeah, it's something that you should know. So this is our integrated rate law. Yeah, so we've derived it. So just make sure the deriving, it's rare that you will be asked, but sometimes you can be told that show that the integrated rate law is this. You have to show all these steps we have written. You first say an imaginary, you put a simple reaction A given B, you write the rate law, you write the rate expression, you equate the two, you make concentration of A to be the subject, to be on one side, you cross multiply, you divide, and you finally apply the definite integrals. Yeah, so I would advise you to you can just pause this video and give yourself a quick recap, try to derive, and then at the end of the day it is important for you to know this formula. Yeah, so make sure you know it. Yeah, you know it well. So this is the integrated rate law. So you can also take note of this expression. We're going to make use of it. Ln A at a particular time over ln O. Ln A initial. Okay, so now having done this, I think it's time to massage our brains. We do a quick question. Let's solve a problem. So this is how simple questions can come. Like they just want to give you a free 5 marks. So they're saying the acid catalyzed reaction blah 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 is a first order reaction. It's now clicking in your mind. Oh, first order reaction. Okay. The rate constant is given. And then for an experiment which was starting when the concentration of hydrogen peroxide was 0.1. Oh, they have given us the initial concentration. Okay, this is good. What is the concentration of hydrogen peroxide after 45 minutes? They have even given us the time. Then, okay. So, what is the concentration when hydrogen peroxide is 45 minutes after the reaction? So just by knowing that it's a first order reaction, we are able to say that this is ln, we're going to say ln A. So the concentration of A at a particular time is equal to negative KT plus ln A. This is the concentration initial. Yeah, so they want us to find how do we say, the rate constant is given, this one is given, time after 45 minutes, they want us to know the concentration. So remember, the integrated rate law shows the relationship of a concentration with respect to time, the rate at which a reaction is progressing. Yeah, so at 450 seconds, what was the time, or what was the concentration? And then the initial concentration is there, it's given. Yeah, so we just plug in and feel happy. So ln A is equal to negative, what is our rate constant? What is the value of K? So the value of K is 1.33 times 10 power negative 4. And then our time is 450 seconds or minutes. And then the initial concentration were given 0.11. So plus ln there 0.11. Okay, so we're going to have ln A is equal to, so what do you get when you say this times that? I'm getting, so I have a negative here. I don't know what it's doing there. So we have 0.05985 plus what is ln 0.11? It's and then what is ln 0.11? So ln 0.11, it's negative. Okay, so I have negative 2.21. If we just end on 3 significant figures. Okay, so now we just continue simplifying. So this will be ln A. Ln A will be equal to, so positive and negative is negative. So here you know that there's a negative. So you're going to simply say negative 0.05985 minus 2.21. You are going to have negative 2.26985. So usually when you're working out problems like this, you don't have to round off to a lot of to a few decimal places. Yeah, you can give your answer as precise as possible, like it's going on, and then you round off in the final answer. Because due to rounding off, if you're rounding off on each stage, like here you just put 0.6, here you put 2.2, your answer can seem to be far from the expected correct answer. So that's one thing to take note of. Okay, so now as we conclude, let's get rid of the ln. So you can say, how do you get rid of the ln? Also, we divide by ln. Yeah, so when we divide by ln both sides, we're going to have concentration of A is equal to, so by getting rid of this ln, it means we introduce a natural logarithm on the other side. So the natural logarithm, and then it will be raised to those things on top there. So negative 2.26985. Okay, so are we together to this point? Yeah, so you have to make sure you understand this lesson. For my own satisfaction, I like to make sure that you've followed. So when you say negative this minus this, you're going to get this value, negative 2.25. They are together. And then ln A, to get rid of the ln, it means we introduce a natural logarithm. That's what has happened. Yeah. So what is the natural logarithm of this raised to that? So I hope you know how to punch that on the calculator. So we'll say the concentration will be equal to, so what is the natural logarithm? The exponential, yeah, whatever you call it, of that number. We're going to get 0.10 103. So this is the concentration. This is the concentration of A when the time was 450 seconds. Yeah. So if you don't know how to punch this, yeah, it's normal not to know. Yeah, you just let me know, like, how did that happen there? I'll be able to attend to you. So inbox me on this line on WhatsApp. Okay, so we're done. That was worth 5 marks. Oh, there was even an equation given. As long as you know the rate shan, if you know this, we didn't even pay attention to the equation, but it's just for you to know. Yeah, can we go to something else? Yes. Okay, so now let's have a look at this question. The reaction 2A is a first order reaction. You have been given a signal, first order. The rate constant is given, and then we have this temperature for no reason. How long will it take for A to decrease from 0.08 all the way up to 0.14? Okay, so this is a very straightforward question. So they are now asking you to find how long. We talked a lot in physics. When you just say how long, you already know that it's the time. So we have ln, let's see, we say ln A. So ln A is equal to negative kt, that k, plus ln A naught. This is the initial concentration of A. So you can as well remember that this this simply means we have ln. So at this point we want to find time. So let's take back ln A to where it came from. So I have ln this A, the final concentration or the concentration at a particular time, minus the initial concentration. Okay. This will be equal to negative kt. Negative kt, like that. So we can make t the subject of the formula. We'll simply say over negative k over negative k, even here, over negative k. So we're going to have ln A. So if you want, you can even simplify. You say this is ln A over A naught. So this will be ln A naught over negative k. So this is equal to t. We've made t the subject. So this is how we're going to solve. So what have we been given? So I think I can erase this. If you are writing as you are following, yeah, you can do that. Okay. So where are we? So we now go to solve the value for time. So the final concentration is this one here, 0.14. So I have ln 0.14 minus the initial concentration 0.08. I mean 0.88 over negative the rate constant 2.8 times 10 power negative 2. So we're finding the value of time. So time will be equal to what are you getting? So make sure on your calculator never punch everything at once. Yeah, except you're using a better programmed calculator. Yeah, so the approach you follow is you say what is ln 0.14 minus, so here I forgot ln, minus ln, oh, I think I'll just solve it with you as an example. So this is how you should be moving. You don't do like everything, just you may end up making mistakes, especially in physics. So ln 0.14, you punch it. Ln 0.14, you get negative 1.97 to 3 significant figures. So this is minus what is ln 0.88? It is negative 0.13. So you should always be careful with the negatives. We already have a negative here, which is this one, and then when you punch in this, you have another negative. So everything is over negative 2.8 times 10 power negative 2. So the time will be equal to so here you already know that it simply means we have a positive, negative and negative. So what is negative 1.97 plus 0.13? You will get negative 1.84. Yeah, so this negative 1.84 over negative 2.8 times 10 power negative 3. So our time will be, the time is, so when you divide, what are you getting, you people? Negative 2.8 times 10 power negative 2. I'm getting 65. I'm doubting my answer. Yeah, so you can solve it through and see what you get. So this is our answer in seconds. Yeah, so we found the time. So coming from, was there any special, like how long? Okay, so they didn't specify like in hours, so this time is in seconds because the rate constant, you can see it as seconds there. So now we can make progress. So one thing to take note is that you can see that they told us, they gave us this concentration, and then we're asked to find the time. So sometimes you can be asked to find the rate constant, this rate constant. So it's now a matter of you manipulating the formula. So you should be able to change things. You make K the subject, you make the initial concentration the subject, and things will be just okay. And then before we proceed, we'll now talk about one thing I forgot to mention when we derived this formula. So the first order reaction is given by ln A. So these are concentrations. So ln A is equal to negative Kt plus ln A naught. So this expression is in form of a straight line, like we can relate it to y is equal to mx plus c. So this is very important, you have to take note. So what does this mean? So these are now common multiple choice questions. they'll tell you that when you have a graph of so this side, so this is the y-axis, so this side will have lane A, on this side, and then on the other side x is t, like the time on that side. So they'll tell you how the graph look. So you observe that k is corresponding with the gradient m, and it has a negative. So always know that the plot of the first order reaction will always decrease, like it's decreasing. Remember we talked about the rate of disappearance. So like the rate constant will be decreasing. So you can be given a number of graphs. They give you one which is looking like this, they give you another one which is looking like that. So always take note. Okay, so that's one thing. So let me even show you something which we're not going to do, but it's worth knowing. So this is a whole lesson. It's not like a short tutorial video. It's a tutorial video, but more of a lesson. I have to teach you in all angles. So what do I want to show you? Okay, so this. Okay, so let's have a look at this not so frequently asked question. So determine if the data below supports the first order reaction. They give you the time. This is the time, and then we have P. So like this is just any reaction, like P is giving us X, or let's say P is giving us Q. So they just didn't want to use A. So now if you'd be asked something like this, what it means, like for you to show that it supports the first order reaction, you would have to plot. So actually sometimes you'd be given to plot. So this means you come up, so time you write it here, and then on this side you put lane P. So you can see here we have P. So you know these people, when they are setting questions, things that don't have to be easy. So they can just give you a column, like they don't give you lane P. So they just give you time and P. So it will not be your job, like you start punching lane 284, you put a value, lane 220 you put, lane 193, just like that. So you don't plot P, you have to put lane P. So and then you would observe that when time is 0, lane P is somewhere 5.6. we can estimate it to be here. So actually answering it, I didn't want to answer. And then when time is 100, so like when time is now 100 seconds, lane P is 5.39. so 5.39, obviously it's reducing. It can't be somewhere here, it will be somewhere there. When time is 150, lane P is 5.26. 5.26 is smaller. And then the next one, 5.41. you can see that the values are decreasing. So, and when you plot a graph, it will be decreasing. So you would conclude that therefore you've shown that this supports the first order reaction. Why? Because of the negative gradient, which can be seen from here. So having mentioned that, now we can proceed. Okay, so now we'll go to what is known as the half-life. The half-life of a first order reaction. So let me quickly take you back to the first page. So you've now understood this formula. You are now experts. You see that looking at it, it's not, you can't remember it very well, at least when you write it over and over. So in our writing, we're putting this negative k to be this side, and then lane A on the other part. So this is we've derived this. So now how does this come about? This is now called the half-life. So I told you that if it's all about knowing the formulas. Yeah, we're almost done, but we have a long way to go because you have to understand each and every part. Okay, so now at this point we're now going to go to the half-life. Yeah, so let's do the half-life of a first order reaction. Yeah, so half-life. So now coming to the half-life, we'll first recall the first integrated rate law. So ln A is equal to negative kt plus ln A naught. So I have ln A naught. This is the initial concentration specifically, and then this can be the final or whatever other concentration at a given time. So now we write this as 80. So what is the half-life? The half-life, from the word half already you have an idea. So the half-life is simply the time taken for the final concentration to be half. So the time it will take for the final concentration to be what? To be half. So what is the formula for the half-life? What are we going to do? So let's make we make T the subject of the formula. Shall we do that? Okay. So we're going to say let's make T the subject of the formula. So we're going to say this part will go to the other side. Okay, so we're going to have kt is equal to ln A naught. Yeah, so we can be putting the brackets ln A naught. So this ln A will go to the other side, it will be minus ln A at a particular time. So and then we can say k is equal to, when we're subtracting logarithms, we know that it's the same as dividing. So A naught over A. Okay, so this is division of these, and then from here now we're going to say k. So before we can divide throughout by k, let us simplify this part. So now the time, now we're going to say 1 over 2. So this is just t and a small 1 over 2 to show that this is the half-life. Half-life, the half-time. Yeah, so I think I was saying the half-life. Where was my mind? Yeah, so that's the half-time for the reaction. So kt here we've just put a subscript 1 over 2. So what does this half-time mean? The half-time simply means that the final concentration, this, what is the time needed for it to be half? So what you have to know is that the final concentration, the time it will be, the time for it to be half, or the point at which it is half, it simply means we are dividing the initial concentration by 2. So what we are saying is this: this is the concentration, like the final concentration, but the half-life, it simply means that we are going to have the initial concentration A naught over 2. Yeah, so even in the second order reaction and the zero order reaction, where there is this A, we'll be substituting with A naught over 2. Yeah, so let's do just that. So we'll say ln, we'll have a there, that's a naught. We'll have a naught over, while there is a for the half time now, while there is this a, we simply say we will put a naught, or put a naught divide by 2. Yeah, so this divide by 2 simply means it's times 1 over 2. A times 1 over 2, it is a over 2. Yeah, so at this point we can simplify. We can simplify to say this is k half time is equal to ln. So let's simplify this. It simply means we have okay, let me omit the brackets so that we work faster. So we have a, this is our a naught. So of course you have to remember we have the brackets. So it simply means we are dividing by a naught over 2. Yeah, that's the meaning of that. A naught over 2. And then this will simply mean we have a naught times what do we have here? It will now be 2 over a naught. You see? Yeah. So this was over 1. And then when we have a division, changes to multiplication. Yeah, I think all this you know. So this simply means that these two are going to cancel. A naught and a naught, meaning we'll just remain with 2. So this means that when you simplify this part, when you simplify everything there, you are going to have 2. Yeah, it simply means that this, so it simply means that this a naught and that a naught will cancel. Yeah. So meaning we'll have ln 2. We're going to have ln 2 there. And then now we can make t the subject of the formula. So the half time will be equal to ln 2 over k when you divide by 1 over 2. Yeah, so this is the formula for the half-life of the first integrated rate law. So what do we have here? So we've now understood how this comes about. Ln half time is ln 2 over k. Yeah, you simply use this, you make it the subject of the formula, and then while there's a, you put a naught over 2, and you're good to go. So just like that, you're fully armed to tackle some silly questions. So speaking of those, let's get to do something. So we're going to answer a question on the half-life. So we'll start with let's see. Okay, we have this question over here. So question 1, we already looked at it in the first lesson under chemical kinetics. I'm sure we're able to answer the average rate. The average in lesson 2, we went through it while we said it's negative change in concentration. So in that case, we have R with respect to time. Yeah, then this is very easy by now. Final minus initial. So our answer in question A2, which was another, they gave it a lot of marks for some reason, as if there was anything involving. So a first order reaction is found to have a rate constant of this. Calculate the half-life of the reaction. So we're going to say the half-life of a first order reaction, it's simply ln 2 over k. Ln 2 over k. So as you do further studying, depending on the reference book you are using, the textbook, the first order reaction, the other formula is where you can punch in advance what is ln 2. So ln 2, so another formula for the half reaction, it's 0.693 over k. Yeah, it simply means they have evaluated this. You punch on your calculator ln 2, it will give you that. So let's answer. So what is ln 2? Ln 2 is 0.693 over the rate constant, it's 5.5 times 10 power negative 14. Yeah, so when you divide, you find your answer. So what are we getting? 5.5 times 10 power negative 14, you'll get about 1.26 times 10 power 13. I won't write that. You can finish, blah blah blah. So this is how easy it can be. Yeah, so we're now going to look at another form of a question which is now more common, because this is a baby question. It is supposed to have like 2 marks. Yeah, but it can be like this. So sometimes you can be told to find the half-life in hours. You have to convert your time which you get here, you convert it to hours. Okay, and then before we even proceed, we're about to conclude the integrated rate law. So we have to take note of the units. This is very, very important. So remember, we said when we have the rate law of a first order reaction, the general form is this. It's power 1. So units are very important. Like, yeah, I think there's even a question whereby they want you to come up with the units. So the units of k, you have to know it very well, because even this question, you know, these people are not nice people. When they are setting questions, they can't tell you that it's a first order reaction. They'll just tell you that a reaction is found to have a rate constant of this. Find the half-life, and we have 3 formulas for the half-life. You want to know, is it the first order reaction, is it the second order reaction? So what should help you is to know the units. Yeah, so this is a mega tip that you have to take note of. Units are very important. The units of k. So how do you know the units of the rate constant? You simply make the rate constant subject to the formula. So this will be equal to rate over concentration of A. So you divide by A, you divide by A, and then you substitute. So this is like dimensional analysis. So we say K is equal to, what is the units for rate? So rate, remember, it's the change in concentration with respect to time. So this means that what are the units for concentration? It's molar, and then time, it's seconds. So the units for rate, I've even explained this in the previous video. So the units for rate, it's molar per second. Yeah, or molar per second, we can write it like this. Molar per second. These are the units for rate. And then what are the units for concentration? It's molarity. And then you can cancel out the m's. Okay, so before I cancel them out, let's see how they are cancelling. So we have K is equal to, this means we have the molarity, molar, molar divided by molar. Molar per second divided by this. And then we're going to say m over s times 1 over m. Yeah, 1 over m. So the m's will cancel. That m and that m. So our units for the rate constant in the first order reaction is 1 over s. And then according to dimension analysis, we learned that this can be written as s with a negative. So these are the units for the rate constant. Here you can see a first order reaction, it has a rate constant of this s negative 1. Yeah, so you can take note of that. It's very important. And one interesting thing as we proceed, if we look at it in a physics aspect, are you observing that the units for the rate constant can actually be hertz? So the units they can be hertz because 1 over seconds, that's the frequency, it's equal to, it's the same as this. Yeah, so but this is not a physics class. It's just something to take note of, like what if your lecturer becomes so crazy that they want you to show the units are his. Okay, so this is it. We can have a look at another question now, which is now a lecturer's favorite. Okay, so what is that question? Okay, so this is a more favorite lecturer's question. Follow me closely on this one. So a certain first order reaction has a half-life of 20 minutes. Calculate the rate constant for this reaction. Okay, so I've been given half-life and it's a first order reaction. So where you see first order, what has to click in your mind? The half-life, we've derived it. Okay, so half-life is equal to 0. What's the figure again? What's ln 2? Ln 2 is 0.693. Okay, so if you want, you can just write ln 2 is the same over k. So we have been given the half-life, it's 20 minutes. So we can make k the subject of the formula, and then we'll proceed to finding. So this is 0.693 over 20 minutes. So what is 0. that divided by 20? 0.963. We're getting 0.048. Okay, so 0.048. So if the time was given in seconds, we could have written per second, but since it's given in minutes, we say per minute. Yeah, that's the half-life, and we're done. Easy and straightforward. Yeah. So now we go to this juicy question. Yeah, this is the interesting part. How much time is required for this reaction to be 75% complete? So we're going to make, so let's remember the integrated rate law. Ln A is equal to negative kt plus ln A naught. So let's make T the subject of the formula. What we're simply going to do is we'll get this KT will go to the other side. We're going to have positive KT. So positive KT will be equal to ln it will be equal to ln A naught minus ln A, like that. And then we can go on to further simplify. So under this, I'm sure you can see that it's more mathematical. Like you just have to manipulate these variables. So KT would be equal to ln A naught over A. Yeah, so when they're subtracting, it means these they can be divided when the logarithms are subtracting. So now what do we have to take note of? This 75% which has been given so here the this 75% complete. So how much time is required? So what you have to understand now at this point is we're trying to find the time. How can we even put it? Okay, so the time required for this reaction to be 75% complete. So like after it has reacted 75%. So so it means that of the final concentration, only 25% has remained. Yeah, you can rewind that one. So we mean the reaction has proceeded 75%, meaning this is what has reacted and it's the time we want to calculate. So it means that the final concentration, so remember this A, ln A, this is the final concentration. It means what is the concentration in the end? So I have the initial and the final. So this means that when the reaction proceeds 75%, then the final concentration has now remained 25% of the initial concentration. Yeah, so let's talk about this nicely. So what we have is the reaction has proceeded 75%. So this is what has been used up. So what it means that the final concentration, what is remaining is 25% of the initial. Yeah, of the initial concentration we started with what? Yeah, so that's that. The final concentration is now 25% of the initial. That's one thing you have to take note of. So what we mean now is that the final concentration that we have, we'll write it. So 25%, when we divide by 100, it's 0.25. So 0.25 of the initial. Initial is A naught. Yeah. So this which we have written is what we are going to substitute now. While is final concentration there, we are going to substitute with this 0.25 of the initial. So let's get back. We are here. So what we mean is that here where this final concentration, we are going to substitute with the 0.25 of the initial. Yeah, so this is like I said, the lecturer's favorite question. Yeah, so you might want to go through it on your own again. So we proceed. We're going to have okay, so say this is kt is equal to it will be equal to ln. So here we have a naught. It will be over here where there is a. Remember saying the final concentration A will be equal to 0.25 because this is what will be remaining, 0.5 of the initial. Yeah, so it's a ln a naught over a naught. It will be 0.25 a naught. Okay. Alright, so we say, I think here you can see very well that the a naughts will cancel. And then we're going to have kt. So we have this kt will be equal to ln. So here it means we're going to have 1 over we're going to have 1 over 0.25. So you can simplify this with your calculator. What is 1 divided by 0.25? You'll find that it's 4. So instead of writing ln 1 over 0.25, the whole lot of this, when you divide, it's 4. So this means that we have ln 4. We have ln 4. So now that's when we can make t the subject of the formula now. So I didn't want to do over t like from this point, or I mean over k. Like it means we're going to have over k. Yeah, we're going to have too many fractions. Yeah, so after simplifying this part now, that's when we can say t is equal to ln 4 over the rate constant when we divide by k. So the time needed to finish up to 75%, it means we get the time which remained now, because 75% the reactants are done. So yeah, we know that only 25% will remain. So this means that the time will be ln 4 over, it will be ln 4 over the rate constant. What did we find? Oh, I've been rubbed, but me also, huh? Yeah, so what did we get here? Yeah, so I'll just redo it. So we just say ln 2 divided by 0. something. Okay, so what was that? So the rate constant, remember to find it, we just said 0.9 or 0.693 divided by 20 because we're given 20 seconds. We found 0.037 347. Yeah, somewhere around this figure. Yeah, so we can just recalculate the value of k. So this means that the time in this point to finish 75%, it's ln 4. So I emphasize, I wish I could capture my calculator. So don't punch on the calculator, you say ln 4 and then you even put divide by this. You go step by step. First punch ln 4, you press equal to. and then you divide by this value now, 0.0347. Yeah, so that you get 39.9, which is approximately equal to 40 minutes. The time was given in minutes. Yeah, so that's how you go through, that's how you solve this. So I emphasize this is the more frequent question rather than the first one. So I had to pick that simple one to give you some confidence. Yeah, but they are all very simple. So now you deserve an exercise, something you can work on. We solved this. Also, this is the simple one, where they give you the rate constant and then they just tell you to find the half-life. And you know that the half-life, it's simply ln 2 over k. Or if you don't want ln 2, you put 0.693 over k. Yeah, that's how we found this. So now where's the question you're going to answer? Okay, so we have these two interesting questions. They are both very okay by now. Yeah, so the first one is exactly like what did you are given, like with 75%, but the time they have just used 320 seconds. So attempt this, and you can show me your work if you feel like. Actually show me your work, it's compulsory. So here there are 2 6s, 5366. Yeah, so I want to see your understanding on this. So let's do it one more time. I'll have this interesting question. So question 1, I think you can now observe that it's common. Like in the first lesson, the introductory lesson, we discussed this. I've even showed you some exam question on this. Yeah, the initial rate, average rate, instantaneous rate, you know all these. So now we're on question 2, and question 3 you can solve after going through lesson 2 in the document. You're able to solve this. Yeah, so you should attempt this, and for this one don't show me, I know you get the concept. Yeah, but you can go through this. So now a first order reaction is 38% complete in 480 seconds. Calculate the value of the rate constant. So the rate constant, this one, by now we can solve it even without thinking. Like you just wake up out of nowhere. So here we say half time is equal to ln 2. I'm emphasizing, if you want you can simplify ln 2 where it gets you to 0.693. So half time is equal to ln 2 over k, and they want us to find the value of k. So the value of k will be, it will be ln 2 over hey, wait a minute, I thought it's easy. So the value of k is ln 2 over what? Over the half time. Okay, so I was rushing, I was like, this is straightforward. So that's when I'm observing that we haven't been given the half-life, so that we find the value of k. So if we're given the half-life, it's just simple, just substitute here where there's the half-life. You say ln 2 divided by the half-life, and then you find. But now in this case, they haven't given us ln 2. They're like, these guys, they think school is easy. We're going to show them. We'll bring the question as if it's easy. Kanshi, it's not very easy, but niche, it's just okay. So this formula won't work because of the half-life not being given. But does that mean that we give up? No. You have to start thinking, this is a first order reaction. the first order reaction, what do I know? I think I know this formula under the first order reaction. Okay, so they want me to find the rate constant, and then at this point you're like, oh, how do I proceed? Yeah, but at least I know the formula. They'll give me 1 mark. But should I end on the formula? No, I deserve better. So want to find the value of the rate constant, this guy. So let's make K the subject of the formula. So we'll say we have KT is equal to, so this is initial. So KT, when it goes to the other side, here will remain with ln A initial, minus ln A, the final concentration there. Yeah. And then we go on to say KT, KT is equal to, here we now understand that it simply means we have ln A naught over A. Yeah. So now we haven't been given the initial concentration, we haven't been given the final concentration. These people, they want us to go crazy. Yeah, so we have been told that the reaction is 38.1% complete. Let me bring down the question here. So where is, okay, so so we're going to say, so here we have been told that it's 38.5% complete, this guy, and the time is 480 seconds. So this 38.5 is what is going to help us here. So what do you have to understand? We now have to remember that, oh, since they have told us that it's complete by 38.5%, so this is what has reacted. So then what is the final concentration? Yeah, I think by now you understand this even very well. Yeah, so since it is complete by 38.5, you subtract that from 100 so that you know what remains. So 100 minus 38.5 is 61. It's 61. My way. 61.5. This is what remained. Yeah, so we use what remained, what is available, so that we know the final concentration. And then we don't write the whole lot of the 61.5% because this is a percentage, so we have to divide by 100. So what is 61.5 divided by 100? You are going to get 0.615. So the final concentration is 0.651 of the initial. In the initial, so this initial from the 100%, so like out of the whole lot of it, the thing that remained is 61.5. Yeah, so this is something you should take note of. When they tell you that no, a reaction was complete by 40%, it means in your calculation what remained, the final concentration, will now be 60% of the initial, and then you divide this by 100. Clear? If not, just send me a here things are not going well, can you explain more? Yeah, we'll roll together. So now let's go on. So the final concentration is 0.61 of the initial. So it means here we'll say KT is equal to ln Lin this here, it's a naught over 0.615 of the a naught, and then we can cancel the a naught. Let's cancel the a naught. Okay, so this calculation, it can go away now. Okay, so what are we going to have? We'll have kt, we're going to have kt is equal to ln. So there, when we cancel, we're going to have 1 over 0.615, and then you know that this is complicated. At least let's divide. What is 1 divided by 0.615? So when we simplify this, we're going to have kt is equal to ln 1.62. Alright, and then let's make t the subject. Wait, oh no, the question is to find the rate constant. Yeah, so we're going to make k the subject. Okay, because t, they've already given us. Where's the calculation again? Let's bring him back. Okay, so we thought this guy is useless. Cash, we still need him. So the reaction is complete in 480 seconds. Yeah, so while there's t, we put 480. So now question go away. We're now going to have k is equal to ln 1.62, like someone's height who is watching this video. Ln 1.62 over t. At least to have solved. I thought I was going to fail, but devil, you are a liar. 1.62 divided by, oh wait, am I talking too much? Yeah, you don't have to take school so serious. Like, you are studying, your face is even looking like, hey, you people. So here, when you put 480, you are going to have 1.005 times 10 to the power -3. So this is the rate constant. And what are the units for the rate constant in the first order reaction? Please, thou shalt know. The units for the rate constants are second per second. So we pronounce this as per second, or we can say second inverse. If the time was given in minutes, you do likewise. If they are crazy enough, they can even give you the time in days. Like, no, ammonia was produced like in 2 days, shan. Then the units for the rate constant will just be days, will be per day, day inverse. Yeah, so some questions, they are so imaginary, just to make your life hell in school. But fortunately, that's why you have me. Okay. So this is the rate constant. I hope we're not wrong. Are we? No. So the caution I would just give you here is when you are working out problems like this, make sure you use as many significant figures as possible as you are solving, and then you round off on the final answer. Yeah, so me, I didn't want to leave this one as 1 point. Yeah, so if we used, like here, I rounded off up to 2 here. If we use this, we could have had a slightly different answer. Yeah, so but as long as your answer is in the range of the expected values, then you are good to go. So let's bring back this question we've been chasing away, and we bring it back. We've answered question A. Okay, we've conquered. Oh, that's not A. A is here. What is the value of the half-life? This is my favorite. Half-life. So when you just see why they are talking about half-life, it's even to start smiling. Instead of solving, you're smiling like, this is my time to shine. There's no way you can feel the half-life, then you should just focus on love. If you feel the half-life. So, but in this question, you can feel the half-life if you didn't get the rate constant correct. Yeah, but the formula is this one. Anyone can master it. If you want, you can be using lean 2. So we're going to say 0.693 over 1.005. I'm too excited. The one I'm even writing. Okay. This is 1 point what? Your tutor should be serious. I'll do better. I was just too excited to find the half-life. Times 10 power 3, blah blah blah. So the half-life is, you just say 0.693 divided by the answer. The figure is very big. It's even scary. Wait. What value are we getting? 0.693 divided by 1. Okay. So, yeah, so this value doesn't look promising. Let's revisit just here. What do we get when we say 1 divided by 0.615? Okay. So, this is why there was a slight mistake. Yeah, so when you divide this by this, the answer is given 1 divided by that, it's 1.626 something. Yeah, so in rounding off, at least I should have put this as a 3. Yeah, so that we continue going on. Yeah, so I think we'll redo this because I don't like the answer we got down there. Yeah. So 1 divided by 0.615. Here it's supposed to be, we'll say lean 1. Now we have lean 1 point. Yeah, so let's even use 1.626. Yeah, at least so this is the part where I said you have to use as much significant numbers as possible. Yeah, so that your answer is making sense. Sometimes if you think about your answer and it's not making sense, you have to think through again. Yeah, so what will be the rate constant? Yeah, so I hope this one will now make more sense. So we say lean 1.626, and then we divide by 480. Yeah, the values are quite okay. So yeah, we're good to go. I was just being a doubting Thomas. So the rate constant, yeah, the same initial value we found was okay. So but solving without rounding off, you'd get 1.01. I think here that's 1.013 times 10 is 2 power negative 3. Yeah, so these are just small variations. Yeah, so even the previous one was okay. So the half-life, which I'm so excited about, it just gave me doubts like things might not be okay. Yeah, but we are just right on track. So this will be 1.0, let's say 013. Yeah, so always remember that when you're doing the right thing, yeah, you'll get it right. They'll see how you're coming and they're like, this one what he or she was doing. So 0. That divided by that would get around 684 seconds. So yeah. Oh, we're now on B. That's the half-life. Wow. All this. And then let's quickly jump to the last one. Wait. We have to do the second order reaction and we're just here. Okay, so I'm about to conclude. Let's see. Yeah, okay. I want this to be a full lesson. I don't want to make it in parts. We make part 1, part 2. Yeah, so better we just do it. I will see how far we'll go. So now the last question, what was it saying? It was saying that how long will it take for the reaction to reach 95% completion? Okay. Like I said, this is the lecturer's favorite. Yeah, because they don't like students to have fun in the exam. They want you to be like, so how long will it take for the reaction to reach 95% completion? What will be the time? Time. Story time. So ln A is equal to negative KT plus ln A naught. By now you know this very well. So let's make T the subject because we want to find the time. So this will be ln. I think by now it's okay if I don't teach you like babies. Yeah. Can I tell you a short story about myself? Let's have a short commercial break. I'm a slow learner, so no wonder you see me repeating things over and over. No wonder you see me talk very slow, because I try to make sure that I leave no one behind. No matter how slow you are, you just know that there's someone who is very slow at learning than you. That is myself, but look at where I am. So now by now you now understand when I write this ln A naught over A, it simply means this has gone to the other side. When it's minus, it becomes a fraction, right? Okay, so the reaction was, how long will it take for the reaction to reach 95% completion? When you just hear that, we're thinking about the final concentration. So since the reaction is 95% completion, it means what is remaining is 5%. So we say the final concentration is 5% of the initial. And we don't write 5%, we divide by 100. So what is 5 divided by 100? You get 0.05. So where there is A here, we're going to say, so I've KT ln we have A naught over, so where there is this A, we put 0.05. Where there is this A, we put 0.05 of that. Yeah, and make sure the ln isn't part of the fraction. It's independent. So when we cancel, we're going to have ln. Yeah, so by now I'm very happy to be teaching now at this point where I can just say this will be ln 20, because I know that my students have understood that when this and that will cancel, here we'll have a 1 divided by this is 20. That's how fast you should be working in the exam. It's okay to be slow at learning. Yeah, as long as you take your time, you understand everything, then you're good. When you master it, you'll be as quick as no man's business. So want to find the time. So we have KT is equal to ln 20, And then now, as my smart students, we are able to know that we can just write this like that. Ln 20 over k. Okay, at this point, I put this question into your hands. You can you can finish up. The rate constant we found. Solve. So we've answered the question. What next? What next? Another question. If this was a live class, this is the part where you hear students be like, no, want to knock off. If you're tired, just pause the video. It won't run away. Go and drink water and you'll find me still talking. This was yeah, my favorite. You see why I was telling you that the units are important. So look at question F. They say study the table below for rate constant k values and then complete it. So just by looking, you see where the units are S inverse upper, you just know that whether they like it or not, I've gotten this one correct. This is a first order reaction. Easy. You see how life is easy when you've understood things. So for the zero order reaction, we'll find the units. Even this one, we'll work it out. Okay, and they were using moles instead of molar. Yeah, these guys were tricky. So the other units here which can be used, they can be something like, okay, we're going to talk about these later. So but you've seen here, you can get it. And then we're not going to answer this whole lot. So let's quickly run through. Of this reaction, the temperature is that, the rate constant is this. What is the order of reaction? What is the order of reaction? So they want you to say, is it a first order reaction? Is it a second order reaction? Is it a zero order reaction? So as a student who passed through Megaminds Tutorial Academy, you should be able to say that the units are S negative or S inverse. This is a first order reaction. They even mark you. They are not selfish. And then what is the half-life of what is this? Sulfonyl chloride at this temperature? What is the half-life? These were very sweet questions. This is the part where you are smiling instead of answering. Have you ever experienced this? So study hard, you will go through such. So the half-life is 0. So because they have said, they haven't said it's a first order reaction, but because of the units, so this is the part where I said the units are important, because if you don't know, you are gone. You can be solving using formulas for the other order. So the half-life is this over the rate constant is that 2.2 times 10. Nish, you are done. Half-life you are found. You just say ln 2, which is 0.693 over the rate constant. Okay, and then how long in hours will it take for 50% of this to decompose? But you even pray that no, this exam was meant for me. I'm getting an A. So how long will it take? You just have to remember this formula we're using. I've even zoomed in so that you can see the sweet question. Ln A is equal to negative KT plus ln A naught. So if you can see that I'm excited, but if you're not clear, you can just reach out. I'll teach you all over, even if it's for 5 hours, as long as you've understood. So how long in hours? Here they were even clever. These people are satanic. How long in hours would it take for 50% of sulfonyl chloride to decompose? So you just have to know that, oh, so 50% was used up, so 100 minus 50 is 50. So this simply means that the final concentration is 50% of the initial. So this is 0.5. So at this point, you can simply say, should we solve this? Yeah, so I'm the type of tutor who doesn't like answering everything. Yeah, because I know that when I teach, you can solve. So this is the part where we say, I'll teach you only like 40%, but you'll be able to answer 90% of a question that can be asked. So how long will it take is the time. So the time, it's kt. So want to make t the subject. So kt comes this side, and then we're going to have ln a over, when this one goes there, this is a naught over a, and then we're going to have kt is equal to ln a naught over 0. I'm now feeling uncomfortable. Are people lost? You shouldn't. Yeah, so this just went to the other side, and then when it becomes minus, it becomes like this. And then the a naughts will cancel. So we have kt is equal to ln, what is 1 divided by 0.5. So the way I'm skipping things here, that's how some lecturers will be teaching you, and you are learning things for the first time, and then you are being taught like experts. So what is 1 divided by 0.5? It's 2. Okay. Okay, so I've ln 2. So we can find the time. It means the time is ln 2 over k. This is more like the half time. Oh yeah, it will be like the half time because it's 50%. Yeah, so we can find this. You just say the rate constant is given, it's here. So ln 2 over that, you've gotten. And then what time in hours does it? They even made the mistake because of preparing funny questions. What time does it take for 25% of the sulfonyl chloride to remain after it decomposes? Okay. They even give it 5 marks. Just know that they want to separate the sheep from the goat. So what time in hours does it take for 25% of this to remain after it decomposes? Okay. So this question is actually, I think it's okay. They just gave it 5 marks to scare you, like 5 marks. No, I think it's hard. I think what I would do would be wrong. Yeah, so don't worry. So what time in hours does it take for this to remain? So here the twist is that by now you've already learned that when they give a percentage, you subtract from 100. Not so. You subtract from 100 so that you know what remained. Like here. Yeah, so just that it was 50. So even if we subtract, it remained 50. Yeah, so but like there we had 75 before. We're using 25% because this is what remained. This went away. So now in this case, these guys, they were clever. They were like, what time does it take for 25% to remain? So this is what will remain, meaning 75% has already gone. So here we don't subtract. Yeah, because they want us to calculate this percentage which remained. So it's like they've subtracted for us in advance already. So we would say this same equation, and then we say ln A is equal to negative kt plus ln A naught. So, and then they want us to find the time. Let's make t the subject. T will be equal to ln A naught. This one goes there. You know the drill over that. And then KT KT will be equal to, so here we're going to say the final concentration that remained is this same 25, because they're telling us that this is what remained. So we say A is equal to 0.25 of the initial. So we say ln A naught over 0.25 of the initial. Yeah. So now at this point we're going to have ln, this one and this one cancel. What is 1 divided by 0.25? It's 4. We have ln 4. So you can find the time. You divide by k. So the time will be ln 4 over k. Ln 4 when you punch on your calculator is 1.38, and then you divide by this rate constant here. Then you are done. Soft life. And this question E, so we're solving just like that. You have learned. Question E, if the temperature is increased from 320 degrees to 420 degrees, the value of K increases by the factor of 4. What is the activation energy? Yeah, so this was a full loaded question. 6 marks. Activation energy, that is a focus for another day. So we'll look at the activation energy in lesson 4, I think. Yeah, after the integrated rate laws, and then that's when we go to the Arrhenius equation. So the Arrhenius equation is where we deal with the activation energy. Yeah, so for now, blah blah blah, we're not solving you. Shame on you. And then this, yeah, that's where we're going. We've already answered, it's the first order, and then we haven't done these two, 0 order and second order. There's even a third order reaction. Wow. We're not learning it. Oh, there's a third order reaction. So for those who be interested, you should tell me I teach you even the 5th order reaction. Let's become crazy. We can even have a 10 order reaction, but the questions which I even had for you, most of them they are 1st order reaction, because yeah, this is the more common concept. It's where everything begins from. Yeah. So is there anything else remaining? We've exhausted the 1st order reaction. After watching this video, you can't feel anything. This question is for exercise, you can solve. Yeah, all the questions I had, yeah, we've hammered them. Yeah, so the 1st order reaction is done. How long is the video so far? 1 minute, 1 hour 53 minutes. Should we do the 2nd order reaction? Yeah, let's go. Don't get tired. 2nd order reaction, I'll summarize it. I don't even have a lot of questions under the 2nd order. So, but I'm sorry for teaching you for so long, okay? In class you even stay longer than this, and worse, in class you won't even be understanding most of the things. Okay. Oh, don't take that to the heart. You know I like joking. 2nd order reaction. What do we know about the 2nd order reaction? So the 2nd order, what do we start with? Oh wait guys, before we proceed, I've just remembered a very interesting question. This is the last question. Yeah, I forgot to highlight this one to you. So let's look at this example real quick. A reaction proceeds through the first order kinetics, first order reaction. The half-life is 180 seconds. What percentage of the initial concentration remains after 900 seconds? Okay, so my aim here is I make sure I teach you in all angles so that you can answer almost any question that can come to you. At least you should be able to answer 80%, 90%. So what initial concentration remains? So here, what initial concentration remains? Oh, what percent? Yeah. So now what you have to understand is that you remember when we are integrating, yeah, going all the way back from there. So the first order reaction, ln A, it was looking like this, minus A naught is equal to KT. Yeah, you recall. So we've just been using whereby ln A is the subject. We take this to the other side. So now when we simplify this even further, when we work backwards, we're going to have ln A over A naught. Yeah, so this is where all these were coming from. Like we made it minus, it went to the other side. So now this part, this same part you are seeing here, this is what shows the percentage. If you're able to work it out, then you solved the percentage. So this is what this question is asking about. So now let's deal with it. He thinks it's clever, but we're cleverer. So the first thing, we have to find the rate constant because it's not given, and this is a first order reaction. It's a first order reaction. When we're given the half-life, we can find this, the rate constant. So the rate constant, we now know that it's 0.693 over T. So you can always interchange these two. If you know the formula for the half-life, whatever I've been written here, so this is 1 over 2. So we're going to have 0.693 over ln 2, okay, over the half time. The half-life, half time, 180 seconds. So what are we getting? 0.693 divided by 180. We get about we're getting 3.85 times 10 power negative 3. So always remember the units for the rate constants under the first order reactions. It's per second. Yeah, so this is the rate constant. So now, having found the rate constant, want to find the percentage after 900 seconds. So we're going to say we know the rate law. We know that the rate not rate law, the integrated first rate law. It looks like this. So let me just write it the way we've known it now. A naught. So when we take this to the other side, it becomes ln A minus ln A naught, and then here we remain with negative T, and then let's simplify here. We are going to have ln A over A naught. It's equal to negative KT. So remember, I introduced this question very well. I'm even proud of myself. When you find this, this is the percentage, this is the ratio of what remains. So let's get rid of the ln. How do you get rid of the ln? You divide by the same ln. Yeah, so I like explaining it like this. I don't know the other mathematical way. So like when getting rid, so when this one cancels, like we're going to remain with a over a naught. It's equal to, so here we're not putting ln. So like in short, I think a better way in which I can explain this is where I say we divide, we introduce a what is this exponential thing? The Euler's constant. Yeah, this guy e. Even here, it means you introduce the same, so that this cancels with this. Or you can say you divide by ln, and then you divide by ln. So, but when you divide by ln, it means you're introducing e. So, this is not a math class. We're not diving deeper. You can just know that when you get rid of a ln, you will remain with e, and then this will be raised to that. I think we even, in this same lesson, we even did something like this. So we're almost done. A over a naught. The doctor's handwriting is now so we have e minus rate constant. Rate constant is 3.85 times 10 power negative 3. Time, they have told us in 900 seconds what is the percentage. So now what do you get when you simplify? A over a naught is equal to negative, this caffeine. First let's simplify what's on top there. Let's say 3.85 times 10 power 3 power negative 3. We multiply by 900, so it means we have negative 3.465, and then we evaluate this. So on your calculator, I don't know what kind of calculator you're using, but you can press where it's written this, and then it has a power x. You just press the button and you write this, negative that. But for a better demonstration, you should text me on WhatsApp if you don't know how to evaluate this one here. So we're going to have what is e to the negative 3.465. We have 0.0313. Okay, so that is the ratio, and then we can convert it to 100. We can convert it to percentage while we multiply by 100. So the percentage is 3.13%. We're done. So this is a very important example. Do yourself a favor, why don't you go through it tomorrow? When you're done with this video, find time to go through it again. Yeah. So now, where do we go next? Yeah, now we can proceed. I now rush you to the second order reaction. Second order reaction. How do these formulas come about? How does the half-life come about? Yeah, so it's going to be so easy. Hold on. So now moving on to the second order reaction, this one. So I took so much time on the first order because like 60% of questions, 70% of questions, they usually come from the first order. Yeah. So now, second order reaction. Let's consider a simple reaction of A giving us B. So, what is the rate law? The rate law is K and A power 2. Do you know why it's power 2? Second order reaction. Yeah, so before we even go further, this time I'll talk about the units in advance. Yeah, so please, the units are very important. They can cost you. You can be given a question. If you don't pay attention to the units, it can be a second order reaction, but you are solving it using the previous equations. Then you automatically get a 0. Yeah, so the units for the rate constant, you simply make K the subject to the formula. So this will be K is equal to over A. Yeah, why do I want to be lazy? So we divide here over this, even here over that. So what are we going to have? We'll have K is equal to rate over concentration of A. So it's just a matter of knowing the concentrations, and this time I'll give you both units. Yeah, for the other one it only has seconds. Yeah, so there are no complications, but here they can trick you so bad. So what are the units for the rate? You know that rate, the units are molar. So this is the first set of units, molar. The rate is molar over, molar per second. That's the rate. And then for the concentration, the units are molar. I hope you know this. We talked about them. Rate, I just like being clear. So rate is the change of concentration with respect to time. No wonder it's molar for concentration over time, seconds. Concentration, the units you know, they are molar. So we can simplify. And then concentration here has a power 2. So we even put it a power 2. So we say we can simplify to say this will be m over s, that on top you divide by m squared. So what are we going to have? We have molar per second times 1 over m squared. So here these will cancel, this and that. Since we have a power 2, it means we're going to remain with 1m. So our final result is 1 over molar second. And in dimensional analysis, I taught you that so these are the units for the constant. So to get rid of the fraction, the powers here will be negative. So it means we're going to have m negative, s negative, and therefore these are the units for the rate constant in the second order reaction. M negative, negative, m inverse, s inverse. Or sometimes if they want to complicate things, they can give you this. They just want to spin your head like, we'll show these students that as lecturers we're more capable. So this is, I'm not attacking the lecturers, I love those people. So yeah, these are the units. And then I also want to show you the other units, because in that table of question they used a different kind of, so these are the units, or these other units also apply. So the rate is equal to the rate constant K. We're saying when we make the subject, it will be like this, over A squared. You see, so here the thing is, the units for rate, we know it's like this, molar per second. But if they want, instead of using molar like this, they'll say instead of molar, where there is molar, they put mole per liter. Mole per liter simply means molar, because concentration is the amount of moles per volume. Yeah, so where there is molar, they can put, we can use moles per liter, and that's how we're going to solve, we're going to derive the other units. So units for rate, we're saying it's mole per so let's write mole per liter per second. Oh way! Of this, I just love being clear. Sorry about me loving repeating things. So this is divided by S. Yeah, so this is where it's coming from. These are the other units for it. Are you confused? You shouldn't be. You are smart, I know you. Molar per liter second. These are the other units for it. Over, so even for the concentration, instead of writing molar like this, instead of writing molar like that, we'll write mole per liter. These are the other units. Yeah, so remember the units are important. Instead of, you can only know these, and then they give you something else and you are stuck, yet you knew everything. So molar here, the concentration for A, it's mole per liter, and then it's having a square. Wow, this is a very ugly expression. I don't like it. So we're going to have mole per, we have liter and second. So this is dividing mole squared liter squared. Simply this. And then we can change the sign. We're going to have mole per liter second times liter squared over mole squared. We've just swapped these two. This one comes down, this one goes there. So at this point we can cancel. More, these two go. L, it goes. And you just getting surprised. Who is this one? Yeah, that's Dr. Megaminds. Unfortunately, this is the only talent I have of teaching, so you bear with me. Actually, this video will go up to 6 hours. Those who hate me, they'll hate me. You can only come and say thank you, or you can come and say thank you after passing. So we have more liter. Here we have only 1 liter remaining, and then here we are remaining with only 1 more. And then the second. So these are the units. And then remember, if you want to get rid of the fraction, according to the dimension analysis in physics and also chemistry. We did so liter per mole. So when we get rid, the things in the denominator should have a negative, should have an inverse. So liter per mole inverse, and then second inverse as well. So these are the other units for the rate constant. It's either this one, which is more cute. We can have this molar second and or molar inverse and second inverse, or this. They are just the same. So let's look at that question we ran through. I hope we'll be able to answer. Okay, so become bigger. Good. So now, wait a minute. Have we made a mistake somewhere? Oh no. Have you seen how these people are so confusing? So at this point, when you look at this, it's there. So this is the part where I was saying you can know these units. You can know these units, and then they give you this. Then you are gone. So, but here they just also, when they used these again, they wanted to be complicating. Like instead of starting with L, because L is the numerator, they start with molar. They write molar inverse, and then that's when they write L, and then that's when they write S inverse. Have you seen when I say that sometimes they act satanic? Yeah, so this is the same. So the answer here is second order. So in life, don't be like lecturers. Although some are good, like myself. Now, majority, we like making life hard. So these are the units. Very important. Very, very, very important. So let's derive the formula. The formula, we have rate. Let's start with this. We say A is giving us B or anything. So let's start with the rate expression. The rate expression is disappearing dA, change in concentration of A, over the change in concentration of time. This is the rate expression. And then now the rate law, that doesn't care much about time. It will just be like K A squared, because it's a second order. So we equate the two. We say negative dA over dt is equal to K A squared. So we've equated this guy to the friend. And then what? We get simplifying. So here again we have to make this one, it should come this side, this one should go there. So when you reach this part, at least these which have concentrations should be together. So upper, I'm going to do it real quick. So we're going to have negative D. So I've changed in A. So now this, when we cross multiply, dt will go to the other side, and then this one, when we divide, it will come down there. Yeah, so I've done it real quick. I think it's time to end the lesson. Yeah, so just soldier on, or almost there. So I have k here, and then dt comes. Yeah, so we just cross multiplied and divided. And then the negative also, we simply say we multiply by negative this side, even on the other side we multiply by negative, which means the negative will go to the right hand side. Here we just want to have the concentrations, so we have that negative. Okay, so now at this point we now do this scary symbol in math. When we start doing integration, it will be fun. Of this integral, so we're integrating from the initial concentration here, from A naught to A final, and then even here from time is equal to 0 up to a certain position. So this is chemistry. We are not going to integrate the whole lot, like, so here what will happen is this and that, this and that. So I gave you a trick. The trick is that just know that d will go, like, this is the importance of that. So this is a Kamega tip. I don't mean that this one cancels with this, but for you to understand better, just say that this will cancel with that. Yeah, there isn't much change. And then the thing which is down here should have a fraction, or should have O. At this point we're going, so when D goes, would have A over A naught. Yeah, so but before that we say A over A squared. The D has gone, even here negative K, the D has gone. So the D has just gone. And here you can see we have two A's, like one should go. So yeah, so we can cancel this and cancel that. Oh, and the other thing I forgot, when there's this integral here on the left hand side, always know that there will be, is it ln? Oh no, there's no ln here. So here we have integrated, so I was giving you a trick that the D will go, and then what will remain of this now is that, so like there will be cancelling, we'll remain with one, and then we'll remain with, here we'll have one concentration of that. So at this point we simply say, so because we're integrating from an initial concentration up to a certain final concentration, so I will say we'll have, so when these cancel, we're going to have 1 over A is equal to negative that. Okay, so now remember that we're integrating from A naught all the way up to a certain concentration. So this means that we have to split this. We'll say it's going to be 1 over the final concentration, and then minus 1 over the initial concentration. So there's no mathematical sense here, it's just to know. Yeah, and then we can make this one the subject, the final concentration. So I have 1 over A is equal to negative KT so this is supposed to be plus. Yeah, so we split this. Yeah, this is supposed to be plus. Hold on. Oh, do I want to confuse myself? Yeah, so it's okay. I think this is a sign that I'm tired. So this is negative 1 over A. When it crosses over, it should be plus. 1 over A naught. A very important expression. So this expression is just like the other one. So this can be written in the form of y is equal to mx plus c. This is a constant. Oh yeah, this can be a constant which cuts the y-axis. So you'll be given, like, they'll give you a, so like a sketch of this, or when you have any given values here on the y-axis, when you have 1 over concentration of A. So meaning here you are sketching against time. So this just looks like the first integrated rate law, because the value of K is negative. So but the only difference is that for the first integrated rate law, it is ln A, but this one is 1 over A. So these are common things you have to take note of. So actually I think I'll formulate a set of questions. Yeah, so we're going to have a test, a Megamind test. I'm going to include these. I put these graphs, like, is this a first order reaction and all that, yeah, so that we enhance your understanding. Okay, so this is the second order reaction. So always remember the first order, this one you can't forget. Yeah, this one we've talked a lot about it. Negative KT plus ln. So the only difference is that this one has fractions, this one has malin. So now we go to the half-life before we do some questions. So what is the half-life of this? Oh wait, let me show you how we're moving. So we've done this one. We've derived, yeah, just like, yeah, positive K. Wait, I made a mistake somewhere. Oh no. Yeah, so it's supposed to be positive K ish. What were we doing? You guys, you couldn't even tell me. Yeah, so here, and on this part, you should always take note that there's no much mathematical logic. So here, here on the negative, yeah, so in the first order reaction with the integration that will follow, we'll discard the negative for some reason. Who knows why? Yeah, so everything is on point except the negative. This guy isn't supposed to be here, so it should just be positive. It should be positive. So this means that the graph, that was a big mistake. Why didn't I even notice? So this is 1 over ln, this is 1 over A. So the graph actually looks like this. It should be increasing, yeah. So it can go like that as long as it's increasing. Yeah, so there was a minor mistake there. At least we've corrected it, eh? Yeah. So that's how the formula comes about. Now let's do the half-life. So how do we work out the half-life? Half-life. So the half-life always know that it's the time for half of the final concentrations to finish. So what is the second order reaction? It's 1 over A naught is equal to KT plus, so this is 1 over A final. So 1 over A initial concentration. So now at this point, so remember for the half-life, when you talk about half-life, we're simply looking at the final concentration. Yeah, so of this final concentration, it simply means the final concentration will replace it with A naught over 2. That's like a simple thing, like a simple trick to know. So we're going to have 1 over, what is A? We say it's A naught over 2. We simply divide the initial concentration by 2. Yeah, so this is equal to KT. So now T is now half. So this is the half time plus 1 over A naught. Okay, so it's just a matter of simplifying here. I'll simplify it on a separate page, and then I'll just come and copy the final thing. Okay, so we have this 1 over A naught over 2. So how do we simplify it? So we're going to simply say, so we have 1 over A naught over 2. So this simply means we have 1, this over we say it's divided by, and then A naught over 2. So this means we're going to have 1 times 2 over A naught. Yeah, and then from there, 1 times 2, it's 2. So we have 2 over A naught. Yeah, so that's the simplified part of this. So 1 over A naught, when you simplify, you are going to have 2 over 1 over A naught over 2, it's 2 over A naught, like this. And then here we have K. Okay, and then before we even do that, let's what are we going to do? We want to make T the subject. Yeah, okay. So let's shift this. It goes to the other side. So we're going to have this will be minus 1 over A naught. This has gone there, it is now minus. It's minus. Yeah. So we have K T. This is half time 1 over 2. So we can simplify this. When you have the same denominator, you simply subtract what's on top. Or if we have a plus, we say 2 plus 1. But we have a minus, we say 2 minus 1, it's 1. Yeah, so this is 2 over A minus 1 over A, it's 1 over A. So this is equal to K and the half time. Okay, so we'll say let's get rid of K. We should just remain with half. So to get rid of K, we simply say over K, and then here you can see there is already over K, so you can simply say divide by K. So when you divide by K, it simply means let's write it properly here. We divide by K both sides. Over and division are the same. So it means we're going to have 1 over A naught times 1 over K when it changes. This is the half time. So in the end, we're going to remain with 1 over. So I was omitting the brackets. They have to be following. Now they are task A naught times K. Or we can better write K in front. So K times A naught, we write the K outside there. We write the K. So this is the half-life. So the half-life is 1 over k and that thing. So half-life 1 over k and then a naught. So I think for this one we'll just do like one example and then we run away from this place. Where is the question? So do you guys hate me for for taking this long? You have to be happy. Yeah. So actually it won't be just one example. I'm sorry. Yeah, so but we'll just do two. The first one will be simple and then the other one will be a lecturer's favorite. Yeah, I have to teach you in this manner so that you are well prepared. So this is why exams seem very hard, because what you will learn will be different from what we expect. The questions in what you would learn in the lecture slides won't be what will come usually. So it'll be like, they don't bring what they teach. They don't ask what they lecture on. So let's quickly go through this. We'll have this. What is this? Nitrosilbromide. Yeah. Yeah, so of nitrosilbromide, and it's a second order reaction. So here this is very important. Next time they won't tell you that it's a second order reaction. They'll just tell you that there's this reaction and then they give you these units. So it's up to you to know that okay, when I have this is a second order. Or if they want to be crazy, they'll give you this. They mean the same. This is what we derived, right? Yeah. And then you saw they can even change, like they put it like this. So these are all the same units. You just have to be smart about it. So a quick mega tip after when you're done with a whole lot of this lesson, you should write the formulas again. Write them over and over. You can stick it in your room, write it on a paper so that you don't forget. Mixing up of these, it's very common. So we have these reactions in second order. If the initial concentration of nitrosilbromide is this, how much nitrogen bromide will be left after a reaction of 10 minutes? Okay, so here they've given us the rate constant is in seconds, they've given us minutes, so we have to convert 10 minutes to seconds. And I think you will help me convert 10 minutes to seconds. What do you get? So on this one, we're going to say these 10 minutes will actually be 600 seconds. Yeah, so we'll use 600 seconds because we can't have, in a formula there's minutes, again there's seconds. Yeah, and it's not easy to change this to molar per minute. No. Okay, so what's the question? How much of nitrosilbromide is left? So they're talking about the final concentration. So we have nitrosilbromide is equal to KT and then plus 1 over the initial concentration of nitrosilbromide. So want to find this final concentration, we have 1 over this, and then it's equal to the rate constant. The rate constant is 0.81. 0 there is insignificant. Time, 10 minutes, we have said we use 600 seconds. Yeah, and then plus 1 over what is the initial concentration. They gave us it's 7.5 times 10 power negative 3. Yeah, so you guys, you have everything here. I think you can manage to continue from here. Yeah, let's rush to something else. We have that. So you multiply here. What is 0.81 times 600? You get 486 plus. So here, because we're using calculators, it's okay if we don't make as a single fraction. You just divide. You say 1 divided by 7.5 times 10 power negative 3. You get 133 something. So you get 133.3. And then you add it to 486. You have 619.3. Is that so? Yeah. And then we get rid of this fraction here. How do we do that? We simply say, where are we going also? So this work isn't looking nice. So I have 1 over this. It's equal to, when we evaluate, we're having 619.3. So you simply cross multiply. Yeah. So when you cross multiply, this will be 619.3. It has multiplied with nitrosyl bromide. This is equal to 1. And then to remain with nitrosyl bromide alone, we divide by this value. Even here, we divide by the same. So meaning the final concentration of nitrosyl bromide. So I didn't even keep my promise. I said you finish. But look at me. I finished with you. This is the love I have for you. So, in order to reciprocate, you should do what? Study hard. So, this is it. We're done. So, but we know they don't ask questions straightforward like this. Like you just get the formula and then you fill in. You think you even get an A+ with a simple question. Yeah, so let's get the lecturer's type of question. The exam kind of, oh, not this one. Okay. So we're doing that. So question B. Oh, and then this one was a nice one. Equilibrium. We're going to, after chemical kinetics, it's chemical equilibrium, where we'll dive into these very nice things. Gacy, reverse reaction, yeah. So a second order reaction is 8.5% complete. We're back to the percentages. So 38.5% complete in 480 seconds. Calculate the value of the rate constant. How do you find the value of the rate constant? So here we'll first recall the formula. So we know that 1 over the concentration of that will be equal to Kt plus the initial. Not so. Yeah, so here we have this percentage. The second order reaction is complete. Okay, so it's complete in 35.8%. Oh, is 38% complete in 480 seconds. At least we know what to put on time. So since we don't have these concentrations, we'll definitely use the ratio. So here, remember, when you have percentages, it means the final concentration, it's a certain percentage of what is left times the initial. So take note of this mega tip. This is not usually taught, but you just have to know, unfortunately. So since it's 38.5% complete, then we divide by, we say 100 minus 38.5, it's 61.5. This question looks familiar. You can find that we were answering it as a first order reaction. Yeah, so this is what remained since it was complete by this much. So we use what remained, and then we make sure we divide that by 100. So what is this divided by 100? We're going to have 0.615. So what is the final concentration? We'll put this. Yebo. So now we'll say we'll have 1 over 0.615 A naught. This is what remained. It's equal to KT KT plus what? Plus 1 over A. So we want to find the rate constant. So the rate constant should be subject to the formula. So we're going to take this to the other side. So what are we going to have when we do that? We have 1 over 0.615 A naught minus 1 over A naught is equal to KT. This K is ugly. And then can we make it as a single fraction? Okay, so here now, what do we do? So these, they won't cancel. There won't be a way to cancel. So we're going to say, so we use this trick. So we say 1, so this is how we can simplify. To make our work easier. Okay, so let's say here, to simplify this, at least we should have the same denominator. So what we will say is, so we have 1 over 0.615. That's 5 and A naught. So this is all the denominator. So we're going to divide this by that. On your calculator, say 1 divided by that. So we divide by that. So 1 divided by 0.615, and then the value we get will be over A. So what does this mean? When you say 1 divided by this, you'll get 0.626, and then it will remain over A naught. So this is the trick which we can use, which we can work with. So remember, this is a lecturer's favorite. Such questions which should spin your head. So this can be written as 0.626 over A naught. And then you might be asking, now why have we done it like that? So that we have the same denominator. That's when it will be easier to work with. Yeah, so here now, when you have the same denominator, according to the rules of operations, the common denominator is basically the same. We have A naught, and then you just subtract. You just subtract those two. Oh, okay, yeah. So it wasn't going to make sense to have a negative. So this is when I'm realizing the mistake. Yeah, so when you divide, it's not giving you 0 point something, it's supposed to be 1. Yeah, so when you say 1 divided by 0.615, it's 1.62. Yeah, so I was going to be like, hey, the easy way of going about it is also giving problems. Yeah, so when we have the same denominator, we can say 1.626 minus 1. What are we getting? We're getting 0.626. So this is equal to 18. So I have the A naught following, and then want to find the value of K. Wait, is it K? Yeah. And then the value of T was given, the time was given. Yeah, was T given? Yeah, definitely. So what is T? We'll replace with 180. So here we'll say this is 0.626 over A naught. It's equal to, so the value of T is 480. So over 480. K. And then to remain with K alone, we say over 480. Even here, we divide by 480. Yeah, I'll say even this side, divide by 480. So meaning we're going to have 0.626 over A naught. So when we say divide by 480, when it changes to multiplication, it simply means we are going to have 1 over 480. So this is equal to K. So yeah, this will be 0.6. This would be 0.626 over 480 A naught. It's equal to K. So I can simplify it whereby we divide 0.626 by 480. We're going to have the value of K as 1.3 times 10 to the power negative 3. So the A naught hasn't gone, it follows down there like that. Yeah, so that's on that. This is the rate constant, and you can put the units. What did we have? Liter per mole. Yeah, those, I think I've forgotten them, but you can't afford to forget. So molar second, yeah, like that. So now let's quickly run to the other one. So how long will it take for the reaction to reach 80% completion? Okay, so what will be the time taken for it to undergo to reach 80% completion. So here you have to remember the equation. So this is equal to kt plus 1 over a naught. So 80% completion simply meaning that the final concentration will be, so since it's 80% completion, this means that what remains is 20, and when you divide 20 by 100 it's 0.2. So what is a final? We're going to put 0.2 a naught, a initial. Okay, so we proceed. We say 1 over 0.2 a naught. So this we can take it to the other side to be minus. So I have 1 over a naught is equal to kt. Okay, and then from here, so at this point you now get the concept of how we can simplify this, because we can't say if this was just a naught we could have said 1 minus 1, but the denominators are not the same. So how you simplify this 1 over 0.2 a naught, you can say what is 1 divided by 2. The answer you get, it will be 5, and then you say over a naught. Yeah, so we'll say this will be 5 over a naught. We've just said 1 divided by this, that's 5. So 1 over a naught, this is equal to kt. So 5 minus 1, it's 4. So 4 over a naught is equal to kt. So we're finding the time. We're going to make k the subject of the formula. So this will be over k. Even here, we divide by k. So it means we're going to have 4 over a naught times 1 over k. Yeah, so here we divided by k, so meaning it was over 1. Yeah, so this will be equal to t, and then from here we can multiply. We're going to have 4 over k and the a naught, it's equal to time. So what is the rate constant? So the rate constant, we found that funny answer 1.3 times 10 or negative 3 a naught. So we're going to say 4 over wait, so hold on. So here this is supposed to cancel. Yeah, so there must be something. Oh, so here we divided. So remember the concept. So when you divide this by that, the answer you get, you put it on the numerator. Yeah, so I put a naught down here. So the value of the rate constant, it's supposed to be 1.3 times 10 something something. It will be over a naught. Yeah, not here where it was written. So if you are writing down as you are following, you can make the adjustment there. Okay, so here we'll say 4 over, so k, the value of k it is 1 times 10 power negative 3 over a naught. Wow, this is the value of k. And then we're also having a separate a naught here. These are all in the denominator. So we have the value of k, this one, which we divided, and then we remember that after dividing we should put it on the numerator. Yeah. So from here we can simplify what's down there in the denominator. We'll simply say we'll have 4 over, so these are multiplying, so they will cancel. And then what is 4 divided by 1 times 10 power negative 3? It is it 4,000? So 4 over this, yeah, I should get something in the range of 4,000. Yeah, so this is the time, 4,000 seconds. Oof. So that's it with the second order reaction. It was a lengthy one. It was worthy 4 marks. Calculate the value of the rate constant. That, yeah, so this is how you can go about the question. So it's prone to error. You can find after solving you made a mistake somewhere, yeah, but you just follow through such concepts. And then finally the zero order reaction. What do you have to know about that? Oh, and as we proceed, I forgot to answer one thing on this example. Yeah, so but you can tackle it. So there was calculate the half-life. So for this second order reaction, you know the half-life, it's 1 over 2 and then 1 over k and then times the concentration. So k was given here, here 0.81, and then also the concentration, the initial, it was given. Yeah, so you can calculate the half-life by just substituting. So now we wind up. So for the zero order, for this one, so I don't even have enough questions under this. So we always start with a simple expression, A giving us B. So what is the rate of the rate expression? The rate expression is negative, it's negative dA over dt, and then the rate law, it's k, and then we have A here. So since it's a zero order reaction, it means it's going to have a power 0. You see that? So we're going to have dA we're going to have dA dt is going to be equal to k. Yeah, because this will just remain 1. And then from here we'll apply the definite integrals from initial to final concentration also here. So you just take note that this dt, it has to go to the other side, and when you introduce the integrals, the d goes, so like would remain with this. And then for the negative, so it's only the second order reaction that doesn't have a negative. So this is going to be negative k. The t comes here, like by means of cross multiplication. And then remember, we're integrating from 0 going up to a certain concentration, from initial to a certain concentration. So we're going to separate this, where we'll say we're going to have A final minus A initial. It's equal to negative KT. Yeah, and then from there we say we can make A the final or the subject of negative KT, and then plus A naught. So when you're told that it's in a zero order reaction, you can use this expression. Yeah, and then for the units very important. So for the units, they come from, so rate, the rate is equal to K, and then we'll have O negative, like that, or power O. So, and then since this will just be 1, also first let's make K the subject of the formula. K will be equal to rate over A power 0. So the units for rate are molar per second. And then since this is just so this is molar per second, these are the units for it. And then the concentration is power 0, meaning it has become 1. It will be 1 and it won't have meaning. So the units for the rate constant for the zero order reaction are just the same units for the rate, which is molar per second, or it can be written as molar per second, like this. Or if they want, instead of writing molar, they will give you mole per liter second. Or if they want to remove the fraction, they'll say molar per liter inverse second inverse. Yeah, so those are the units. And then now quickly rush into the to the half-life, or sometimes I call it the half-time. So about the half-time, you just have to understand that where there is final concentration, we simply put A over 2. Yeah, so that's for the half-time. So here, where there is final, we'll put initial. So to derive the formula, we'll say A initial over 2. Yeah, A initial over 2, and then this can go to the other side. No, so because here we have a negative, so we're going to take, first let me write KT plus A initial. So let's take this to this side and then this to the other side. We're going to have KT, so T is now the half time. So we're going to have KT is equal to, we have A naught minus A naught over 2. So KT is equal to, when we make the subject of the formula, we're going to have common denominator 2 times A naught, it's 2 A naught minus A naught, So on there on top our like so this it's just the basic form, like here on such things, like we just divide this by that and then it remains the numerator. Yeah, so it has roots coming from the basic applications. So we have kt is equal to 2a minus 2a, it's 1a. So we have a naught over 2, and then to remain with t alone, so which is the half time, to remain with t alone, we say we divide by k. We divide this side by k, even this side we divide by k. So this means that the half time will be equal to it will be equal if so let's, where are we? Okay, so I think this is a sign that we should conclude as early as possible. Yeah, so we're done. We're just deriving the formula. So we're going to say here I've divided by k. This is looking like a 4 here. So we've divided by k. So we're going to say this will be a, it's going to be a, what's wrong with this? A naught over 2 times 1 over k. Yeah, because here there's an imaginary over 1. Okay, and then we're done. The half time is a naught over 2k. So the half time for a zero order reaction is that. So this was quite an exhausting lesson. So what did I do? Oh, it's this one here. So I was looking at this as the zero order reaction. So the zero order reaction is here, the half-life a over 2k, a naught over 2k. Yeah, so that's it. We're going to give you some work in the later on as we progress with our lessons. Yeah, so I only had this question. It was a zero order reaction, but it doesn't have the applications of what we've talked about. So this is more applied in the rate expression. Yeah, so but they said it's a zero order reaction, and then write the rate expression in terms of ammonia, nitrogen, and hydrogen. So the rate expression, you have to start writing. So the rate of ammonia, with rate expression, is it rate law? Yeah, so but you have to start writing rate expression. So for ammonia, I would say negative 1 over 2 change in change in ammonia. Yeah, just like that. Here for the products, you know they will have a positive. So calculate the rate of formation. So this is in lesson 3 where we looked at this. Yeah, so we'll continue up with the lessons that follow. So next we'll get to look at the Arrhenius equation, where we deal with the activation energy. So in this lesson we have achieved what I planned on highlighting. We started with the most important one, and then the second order, and then this one, zero order. So I told you we can have third order, we can have fourth order. So if you want, you can explore. You just write A is giving you B, and then you go on to say the rate will be K, the concentrations will be according to the order, like if it's power 3, power 4. So this is where we end with this video. This lesson we've covered quite a lot. So if you have any problem somewhere where you feel like I don't know what happened, or you feel there might be a mistake, you're like, are you sure what you did is just okay? So you can just let me know. We learn together. So this is where our lesson ends. I'll see you in the next lesson, and that's it.